Welcome to today's session. In this video, we'll tackle problem number 638, shopping offers. This problem challenges us to optimize the cost of purchasing items by effectively applying special offers. We'll explore different approaches, analyze their complexities, and arrive at an efficient solution. Let's dive in. In this problem, you have a shopping task where you want to purchase specific quantities of items, and each item has a fixed price per unit. To help reduce costs, there are special offers available. These offers bundle certain quantities of items together at a discounted price. Your objective is to figure out the minimum cost required to buy the exact quantities of items you need. The inputs include three key components. First, there's the price list, which tells you the per unit price of each item. For example, if the price list is 2.5, it means the first item costs $2 per unit and the second item costs $5 per unit. Next, there's special, which is a list of discounted bundle offers. Each special offer specifies how many units of each item are included in the bundle and the total cost of the offer. Finally, there's needs, which outlines the exact quantities of each item you need to purchase. The goal is to calculate the minimum cost to satisfy these needs using any combination of individual purchases and special offers. Let's look at the first example to understand how the inputs and outputs work. Here, the price list is 2.5, meaning the first item costs $2 per unit and the second item costs $5 per unit. The special offers are 3, 0, 5, 1, 2, 10. The first offer gives you 3 units of the first item for $5. And the second offer gives you 1 unit of the first item and 2 units of the second item for $10. Your needs are 3, 2, which means you need 3 units of the first item and 2 units of the second item. To minimize the cost, you can purchase the first special offer, which fulfills the need for 3 units of the first item and costs $5. Then, you buy the remaining 2 units of the second item individually, which costs $2 per unit, totaling $10. Adding these together, the total cost is $14. Now, consider the second example. Here, the price list is 2, 3, 4, meaning the first item costs $2, the second item costs $3, and the third item costs $4 per unit. The special offers are 1, 1, 0, 4, 2, 2, 1, 9. The first offer provides 1 unit each of the first and second items for $4. The second offer provides 2 units each of the first and second items, along with 1 unit of the third item, for $9. Your needs are 1, 2, 1, meaning you need 1 unit of the first item, 2 units of the second item, and 1 unit of the third item. To minimize the cost, you can buy the second special offer. This offer includes 2 units each of the first and second items, and 1 unit of the third item, for a total cost of $9. Even though this exceeds the need for the first item, you must buy the entire offer as fractional purchases are not allowed. Therefore, the minimum cost to fulfill the needs is $11. While solving this problem, you need to consider several edge cases. First, if no special offers are available, you must calculate the cost purely based on the per unit price of each item. Second, some special offers may include more items than you need. Since offers must be purchased in whole, you'll need to carefully evaluate whether such offers are worth using. Third, if all the quantities in the needs list are 0, the cost should be 0 because no items need to be purchased. Finally, there could be multiple ways to achieve the same minimum cost. In such cases, any valid combination of purchases that results in the minimum cost is acceptable. These considerations are critical for ensuring your solution handles all scenarios correctly. To begin solving this problem, let's first consider the brute force approach. The intuition here is simple. We try all possible combinations of applying the special offers and calculate the total cost for each configuration. This involves recursively exploring every way to purchase the items, both with and without offers, while keeping track of the minimum cost encountered. There are some key observations about this approach. Each special offer can either be applied, assuming it is valid for the current state, or skipped entirely. This creates a decision tree where every branch represents a potential path. While calculating the total cost without any offers is straightforward, the challenge comes from the sheer number of combinations to explore. The computational complexity grows exponentially as the number of offers increases. In the worst-case scenario, we might need to explore O2 to the power of the number of offers, subsets of offers. This makes the brute force method impractical for larger inputs, as the recursion depth can quickly become overwhelming, especially when dealing with multiple items and quantities. Now, let's look at how we can optimize this process using recursive backtracking with pruning. Instead of blindly exploring all possible combinations, this approach employs several techniques to make the search more efficient. First, we prune invalid paths early. If a special offer requires more items than we need, we can skip it entirely. Second, we use memoization to cache results for specific states, defined by the quantities of items remaining. This avoids redundant calculations for the same state. Third, we prioritize offers with higher savings, which reduces costs more effectively in the early stages of the decision tree. This transforms the problem into a state space search, where each state represents the current quantities of items left to purchase. By caching results for these states, we drastically reduce the exponential growth in computations. The time complexity here is approximately O, max quantity per item raised to the power of the number of items, thanks to memoization. This is a significant improvement over brute force. We should also note that while dynamic programming could be an alternative, it is less natural for this problem due to the challenges of iterating over both offers and item quantities simultaneously. The time complexity for this optimized approach remains roughly O, max quantity per item to the power of the number of items, similar to the recursive backtracking with memoization strategy. However, dynamic programming, while theoretically equivalent, is less intuitive and harder to implement for the structure of this problem. With that in mind, the chosen strategy is recursive backtracking with memoization. This method strikes the right balance between simplicity and efficiency. It leverages the recursive structure of the problem to adapt to different inputs while avoiding redundant calculations through memoization. There are several reasons why this strategy works well. First, it is efficient. Memoization eliminates duplicate work, and pruning ensures we avoid unnecessary paths. Second, it is flexible, as the recursive design naturally accommodates variations in the number of items in offers. Lastly, it is clear and relatively straightforward to implement compared to dynamic programming. Of course, there are trade-offs. While the worst-case time complexity is still exponential for very large inputs, memoization ensures the solution remains efficient for most typical constraints. Brute force is simpler to conceptualize but unusable for larger inputs, while dynamic programming, though equivalent in theory, is harder to implement cleanly. The key insight, or the aha moment, behind this approach lies in recognizing that the problem revolves around its state space, which is defined by the remaining quantities of items to purchase. By caching results for these states, we avoid resolving identical subproblems. This realization transforms the problem into one that is both elegant and computationally efficient. The ability to reuse results ensures that we are not repeatedly performing the same calculations, which is what makes this strategy so powerful. This focus on states allows us to seamlessly merge the recursive structure of the problem with the optimization techniques of memoization and pruning, delivering a solution that is both effective and easy to reason about. The problem we're tackling involves a shopping scenario where you aim to minimize costs while fulfilling a shopping list. You have two ways to buy items: purchasing them individually at their given prices, or using special offers, which bundle certain quantities of items at a discounted price. The inputs include the price list, which tells you the cost of each item individually, the special list, which details the bundles available and their costs, and the needs list, which specifies the quantities of each item you must purchase. The goal is to determine the lowest possible cost for fulfilling the requirements and needs using any combination of individual purchases and special offers. To solve this problem, we can start with a recursive brute force approach. The base case is simple: if all the required items and needs are zero, meaning there's nothing left to buy, the cost is zero. For the recursive case, we evaluate each special offer to see if it can be applied. A special offer is valid if the quantities in the offer do not exceed the current needs. If valid, we subtract the offer's quantities from needs and calculate the cost for the remaining requirements recursively. We also calculate the cost of satisfying needs without using any special offers by purchasing items individually. Finally, we return the minimum cost among all these possibilities. To improve efficiency, we can prune invalid offers, those that exceed the needs, and use memoization to store the results of previously computed states. By representing needs as a tuple, we can use it as a hashable key in a hash map, allowing us to quickly retrieve stored results and avoid redundant calculations. The implementation begins with pre-processing the special offers to filter out those that aren't cost-efficient. For example, if a bundle's cost exceeds the sum of buying its items individually, it can be ignored. We then define a recursive helper function, commonly called DFS, which takes the current state of needs as input. The base case checks if all items in needs are 0, in which case the function returns a cost of 0. Using memoization, we check if the current state has been computed before and return the stored result if it exists. The function evaluates the cost of all valid special offers and compares it with the cost of buying items individually for the current needs. The minimum of these costs is stored in the memoization table and returned. This approach ensures efficient exploration of all possibilities while avoiding redundant computations. There are several key insights that make this approach effective. First, pruning the recursive tree by skipping invalid offers significantly reduces the search space, as we only evaluate offers that can actually be applied. Second, memoization ensures that each unique state of needs is computed only once, which drastically improves performance. Third, representing needs as a tuple makes it easy to compare states and use them as keys in a hash map for memoization. Edge cases are also important to consider. For instance, when there are no special offers available, all special offers exceed needs, or certain items in needs are not covered by any special offers. Addressing these cases ensures the algorithm handles all possible scenarios robustly. To efficiently implement the solution, we use key data structures. The needs list is converted into a tuple because tuples are immutable and hashable, making them ideal for memoization. The hash map, or dictionary, stores the computed minimum cost for each state of needs, enabling rapid lookups during recursion. The input lists for price, special, and needs are straightforward for storage and iteration. Analyzing the algorithm's complexity, the time complexity depends on the number of items n and the number of special offers m. The total number of states is proportional to max_needs, n, where max_needs is the maximum quantity of any item. For each state, we evaluate up to m special offers, leading to a total time complexity of O, m*, max_needs, n. The space complexity is dominated by the memoization table, which also has a size of O, max_needs, n. To bring the algorithm to life, let's walk through an example. Suppose the price list is 2, 5, the special list contains two offers, 3, 0, 5, and 1, 2, 10, and the needs are 3, 2. Starting with needs equals 3, 2, we evaluate the first offer, 3, 0, 5. This bundle satisfies all three units of the first item, leaving needs equals 0, 2. Next, we evaluate the second offer, 1, 2, 10, which reduces needs to 2, 0. For each of these new states, we compute the costs recursively. Finally, the algorithm compares the total costs of all valid combinations and returns the minimum cost, which in this example is 14. This demonstrates how the algorithm balances special offers and individual purchases to find the optimal solution. Here, we start by importing the ru_cache decorator from the functools module, which will help us optimize the recursive function through memoization. Then, we define the shopping offers method within a solution class. This method takes three arguments: price, which is a list of individual item prices; special, which is a list of special offers where each offer specifies quantities of items and the total price for that offer; and needs, which represents the quantities of items we want to purchase. Next, we define a helper function called direct_purchase_cost. This calculates the total cost if we were to buy all the items at their regular prices without using any special offers. It uses a generator expression to multiply the number of items needed by their respective prices and sums up the results. The core of the solution lies in the DFS function, which is decorated with a ru_cache to store and reuse results for previously computed states. This function takes the current state of needs as an argument and starts by calculating the cost of fulfilling the needs without any special offers by calling direct_purchase_cost. We then initialize min_cost with this direct cost. For each special offer, we check if it can be applied by iterating through the items in current_needs and the quantities in the offer. If at any point the offer requires more items than what we currently need, the loop breaks and the offer is skipped. However, if the offer is valid, we calculate the updated needs by subtracting the offer quantities from the current needs. After that, we make a recursive call to DFS with these updated needs and compare the resulting cost with the current min_cost, updating it if the new cost is lower. Finally, the function returns the minimum cost found. The DFS function is then called with the initial state of needs, which is converted into a tuple to make it hashable for the ru_cache. The result of this recursive function is returned as the final answer. This approach ensures that we explore all possible combinations of applying special offers, while the memoization significantly reduces redundant computations. The solution is both efficient and elegant, leveraging recursion and dynamic programming principles to handle the problem's complexity. With this implementation, we can minimize the total cost of shopping while considering all the constraints provided by the input. Here, we start implementing the solution for the shopping offers problem in Java. First, we import the necessary utility classes and define the solution class. Inside it, we have the main method, shopping offers, which takes 3 parameters: the price list of individual items, the list of special offers, and the list of needs that specifies the quantity required for each item. To begin, a helper function named directPurchaseCost is defined. This calculates the total cost if no special offers are applied. It iterates over the needs list, multiplying the quantity of each item by its price, and accumulates the total. Next, we set up a memoization map, memo, which will store computed results for specific states of needs, helping us avoid redundant calculations. Finally, a recursive function DFS is introduced to explore all possible ways to fulfill the needs. It begins by checking if the current state of needs has already been computed and stored in the memo map. If so, the pre-computed value is returned. Otherwise, it calculates the cost of fulfilling the needs without using any special offers by calling directPurchaseCost and stores this as the initial minimum cost. Now, the function is set up to attempt applying each special offer one by one. For each special offer, the algorithm creates an updated needs list and checks if the offer can be applied. This is done by iterating through the current needs and comparing them with the quantities in the offer. If the current need for any item is less than the quantity provided by the offer is deemed invalid and skipped. On the other hand, if the offer is valid, the updated needs list is calculated by subtracting the quantities in the offer from the corresponding current needs. The cost of applying the offer is then added to the result of a recursive call to DFS with the updated needs. This cost is compared with the current minimum cost, and the lower value is retained. After trying all the special offers, the minimum cost for the current state of needs is stored in the memoization map to optimize future calls. Finally, the recursive function returns the minimum cost. At the end of the shopping offers method, the DFS search is initiated with the initial needs list, and the result is returned as the minimum possible cost to fulfill all the needs while utilizing the available special offers. Here, we begin with a basic example to understand the approach. We are given the prices of items as 2, 5, 1 special offer, 1, 1, 4, and the needs 1, 1. The first step is to calculate the direct purchase cost, which is simply the cost of buying the items without using any special offers. This is calculated as 1*2 plus 1*5 equals 7. We initialize min_cost to 7, as this is the baseline cost without any offers. Next, we consider the given special offer, 1, 1, 4. To determine if this offer is valid, we check if we can fulfill it with our current needs. Since 1 equals 1 for both items, the offer is valid. We then subtract the quantities in the offer from the current needs, resulting in updated needs of 0, 0. After updating the needs to 0, 0, we make a recursive call to the DFS function with these new needs. At this point, since the needs are 0, 0, we hit the base case where no items are required. The direct purchase cost for 0, 0 is 0, so the function returns 0. We then calculate the total cost of using this special offer, which is the offer cost of 4 plus the cost of fulfilling the remaining needs, which is 0. This gives a total cost of 4. Now, we compare this cost of 4 with our previously initialized min_cost of 7. Since 4 is smaller, we update min_cost to 4. Finally, the minimum cost to satisfy the needs with the given prices and offers is determined to be 4. In this second example, we have item prices 2, 3, 4, 2 special offers 1, 1, 0, 4, 2, 2, 1, 9, and the needs 1, 2, 1. First, we calculate the direct purchase cost 1 * 2 plus 2 * 3 plus 1 * 4 equals 12. We initialize min_cost to 12. Then, we evaluate the first special offer 1, 1, 0, 4. To check if this offer is valid, we compare its quantities with the current needs. Since 1 equals 1, 1 equals 2, and 0 equals 1, the offer is valid. Using this offer results in updated needs of 1 to 1, 2 to 1, 1 to 0, which simplifies to 0, 1, 1. With the updated needs 0, 1, 1, we make a recursive call to the DFS function. Here, the direct purchase cost for these needs is calculated as 0 * 2 plus 1 * 3 plus 1 * 4 equals 7, and the function returns 7. Now, the total cost of using the first special offer is the offer cost of 4 plus the cost of fulfilling the remaining needs, which is 7. This results in a total cost of 11. We compare this with our current min_cost of 12 and update min_cost to 11. Next, we consider the second special offer, 2, 2, 1, 9. However, the current needs, 1, 2, 1, are not sufficient to use this offer, so we skip it. The final minimum cost remains 11. In this example, the item prices are 3, 4, there is one special offer, 1, 1, 5, and the needs are 2, 2. First, we calculate the direct purchase cost as 2 * 3 plus 2 * 4 equals 14. And we initialize min_cost to 14. Now, we evaluate the special offer 1, 1, 5. To check if it is valid, we verify that the quantities in the offer do not exceed the current needs. Since 1 equals 2 for both items, the offer is valid. After applying this offer, the updated needs are 2 to 1, 2 to 1, which simplifies to 1, 1. With the updated needs 1, 1, we make a recursive call to the DFS function. Here, the direct purchase cost for these needs is 1 * 3 plus 1 * 4 equals 7, and the function returns 7. The total cost of using the special offer is the offer cost of 5 plus the cost of fulfilling the remaining needs, which is 7. This gives a total cost of 12. We compare this with our initial min_cost of 14 and update min_cost to 12. The final minimum cost to satisfy the needs with the given prices and offers is determined to be 12. The time complexity of our solution is primarily influenced by the depth of the recursive DFS function and the operations performed during each recursive call. First, let's consider the number of recursive states. The DFS function is memoized, meaning that each unique state of current_needs is computed only once. The total number of these unique states depends on the maximum possible values for each item in the needs array. If there are n items and the maximum quantity required for each item is capped at m, the total number of states will be roughly m⁻n. Now, for each of these states, we process all k special offers. For each special offer, we need to determine whether it can be applied, which involves iterating through all n items in the needs array. This operation takes n time. Therefore, processing a single state has a complexity of k*n. To calculate the total time complexity, we multiply the total number of states by the time required to process each state. Since there are up to m⁻n states and processing each state takes k*n time, the overall time complexity becomes m to the power of n times k times n. Now, let's examine the space complexity. The memory usage is primarily determined by the memoization table and the recursion stack. The memoization table stores the results of the DFS function for all unique states. Each state is represented as a tuple of size n, and with up to m⁻n unique states, the memory required for memoization is m to the power of n*n. Additionally, the recursion stack depth corresponds to the sum of all values in the needs array, which in the worst case is bounded by n*m. This means the recursion stack consumes n*m space. Together, these factors dominate the space complexity. There are also minor additional space requirements for variables and intermediate calculations, but these are negligible when compared to the memoization table and recursion stack. Therefore, the total space complexity is dominated by the memoization table, resulting in m to the power of n*n. Comparing this approach to a brute force solution highlights the efficiency of our algorithm. A brute force approach would involve generating all possible combinations of applying special offers to satisfy the needs. This would require exploring all subsets of the state space, leading to a time complexity of k plus 1, n*m, where k plus 1 accounts for either applying a special offer or not. In contrast, our recursive memoization approach avoids redundant computations and reduces the number of explored states, achieving a significantly improved time complexity of m to the power of n times k times n. This optimization is key to making the solution practical for larger inputs. Now, let's analyze the algorithm in terms of best, average, and worst-case scenarios. In the best case, the needs are small, and the special offers align well with the requirements, leading to minimal recursion depth and fewer states. The worst case occurs when the needs array is large, and there's little overlap between the special offers and the requirements. This forces the algorithm to explore the full state space, resulting in the maximum time complexity of m to the power of n times k times n. On average, the runtime is influenced by the degree of overlap between the special offers and the needs. However, due to the exponential growth of the state space, the average case often trends closer to the worst case complexity. Mathematically, the DFS function evaluates all valid states of current_needs, which are bounded by m*n. For each state, it iterates over k special offers and checks their validity in n time, leading to the overall time complexity of m to the power of n times k times n. The space complexity, primarily driven by memoization, remains m to the power of n*n. When tackling the shopping offers problem, there are several common mistakes to be mindful of. One major pitfall is ignoring edge cases. For instance, scenarios like zero quantities, where no items need to be purchased, or situations where no special offers apply, need to be handled carefully. Similarly, when all the special offers end up costing more than the base price, your solution should account for this to avoid unnecessary computation. Another frequent issue is the mishandling of overlapping or redundant special offers. Applying an offer that partially satisfies another can lead to suboptimal results, so it's important to evaluate offers in a structured way. Inefficiency is also a concern. Brute force approaches might work for small inputs, but as the problem scales, they become computationally expensive. This is particularly true for constraints where inputs can go up to 10,000, and unoptimized recursion or repeated calculations can cause timeouts. Additionally, if the state in your dynamic programming solution is misrepresented, say, through ambiguous variables or poor indexing, it can make debugging difficult and lead to incorrect answers. Finally, failing to prune non-promising paths, such as applying offers that result in negative quantities, can waste valuable computation time. Efficiently managing these aspects is key to solving the problem effectively. Now, let's focus on some key insights that can be valuable during interviews. First, optimizing recursion with memoization is crucial for problems involving combinations. Memoization ensures that you don't solve the same sub-problem multiple times, which significantly improves the efficiency of your solution. It's also important to pay close attention to the problem constraints. Interviewers often design edge cases to test your understanding, so knowing the input limits and ensuring your solution handles extreme values is essential. Another critical aspect is how you represent the state. You need to clearly define how quantities, items, or offers are represented and ensure that transitions between these states are both valid and efficient. Be prepared to discuss trade-offs as well, for example, why you might prefer a dynamic programming approach over brute force. Highlighting the differences in time and space complexity shows your ability to evaluate solutions critically. Finally, it's a good idea to start with a straightforward brute force solution. This demonstrates that you understand the problem, even if the solution isn't optimized yet, before you move on to more advanced techniques. Next, let's look at some related problems that share similar concepts. Of course, LeetCode 638, the shopping offers problem, is a classic example that involves minimizing the total cost using dynamic programming and recursion. Another related problem is LeetCode 416, partition equals subset sum, which also requires selecting subsets optimally to achieve a specific goal. Then there's LeetCode 322, coin change, which focuses on minimizing the number of coins needed to achieve a target amount, and LeetCode 518, coin change 2, which builds on this idea but shifts the focus to counting all possible combinations rather than minimizing the number of coins. These problems share foundational techniques like dynamic programming and recursion, making them excellent practice for building a deeper understanding of how to approach combination and optimization problems. Finally, let's explore some alternative approaches to solving the problem. One option is backtracking with pruning. Instead of exploring all possible combinations, you can prune paths that exceed the target or lead to infeasible states. While this approach is slower than dynamic programming, it's often simpler to implement for smaller inputs. Another method is dynamic programming with a top-down approach. By applying memoization, you store intermediate results, which eliminates redundant computations and is generally more efficient for larger inputs. Alternatively, you can use a bottom-up dynamic programming approach, where the solution is built iteratively. This has the advantage of using less stack space compared to recursion, though it can be more challenging to define and manage the state space. Lastly, there's the greedy approximation approach. In some problem variations, choosing the cheapest offer first might yield an acceptable solution. While this method isn't always optimal, it can be significantly faster and works well in cases where the problem satisfies the greedy choice property. Great job following along. Today, we reviewed problem number 638, shopping offers, and learned how to approach optimization problems step by step. Remember to practice breaking problems into smaller parts and understanding the trade-offs between brute force and optimization. If you found this helpful, please like, subscribe, and share. Thank you, and see you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!